Hello everyone, welcome back to Code Oris. In our last video, we explored the fundamentals of the Model Context Protocol, or MCP. We discussed what MCP is and why it's important. We also went through how the MCP server works and how it's shaping the future of contextual AI integrations. Additionally, we got hands-on with the MongoDB MCP server demo to see it in action. If you haven't watched that one yet, I highly recommend checking it out first. It'll give you a solid foundation before diving into today's topic. In this video, we are going one step further. We will actually build a working MCP server from scratch. You'll learn how to implement, configure, and test your own server using the MCP Inspector tool. So by the end, you'll have a fully functional setup ready to integrate with your model environment. So before we dive into the code, let's quickly recap what MCP is all about. The Model Context Protocol is an open standard designed to help AI models access and interact with real-world data sources, APIs, and tools in a structured and secure way. Instead of relying on ad hoc prompts or plugins, MCP allows models to communicate with external systems using a consistent protocol, enabling reusability and better context management. It solves key problems like context fragmentation, data isolation, and inconsistent API behavior, making it easier to build scalable, multi-model integrations across your ecosystem. Now, let's understand how an MCP server actually works behind the scenes. At a high level, the MCP server is made up of a few key components that work together to let your model talk to real-world systems in a structured and reliable way. First, the server core. This is the central hub that handles all incoming MCP requests that come from the client or model environment. For example, when a model wants to retrieve data, execute an operation, or trigger an external API. It manages the request routing, ensures the communication follows the MCP protocol, and decides which handler or adapter should take care of the job. Next, we have the handlers, also called adapters. Each handler is responsible for a particular type of request. For instance, one handler might fetch records from a database, another might send an API call to a service, and another might run a custom computation. They translate high-level model requests into actionable logic, bridging the gap between what the model asks for and how it's executed in the real world. Then we've got the data sources or APIs. This is where the actual information lives. These could be your databases, like MongoDB, PostgreSQL, or MySQL, or even REST APIs, cloud services, or any external data system. The MCP server connects to these systems to retrieve, update, or process data as requested by the handlers. And finally, the response layer. Once a handler finishes its work and gathers the result, the response layer steps in. Its job is to take that raw output, whether it's data, a message, or a computed value, and format it properly according to MCP standards. This ensures the response is well-structured, consistent, and easily understood by the model or client. So, putting it all together, the server core routes the request, the handlers do the work, the data sources provide the actual information, and the response layer sends everything back neatly to the model. That's the big picture of how an MCP server operates behind the scenes. Now let's talk about Model Context Lifecycle. It defines how the model, the MCP server, and the surrounding environment interact from start to finish. Let's walk through the three main phases step by step. It all starts with context initialization. This is where the model sets up the environment it wants to work in. During this stage, the model defines the context, which might include specifying which MCP server to connect to, what capabilities it needs, and what type of requests it plans to make. Essentially, it's laying the groundwork, making sure the model and the MCP server are on the same page before any requests start flowing. Once the context is initialized, the model moves to the context request phase. The model sends a structured request to the MCP server, for example, asking for specific data, triggering a computation, or executing a command. The MCP server's server core receives that request, routes it to the right handler or adapter, and the handler takes care of the task, whether that's fetching records, querying an API, or performing some business logic. Finally, we have the context response phase. Once the server finishes processing the request, it sends back a response. The response layer formats the data into a well-structured MCP-compliant message and sends it back to the model. The model then updates its internal context, meaning it now has the latest information or state needed for the next action. This cycle, context initialization, request, response, repeats every time the model interacts with the MCP server, keeping the system dynamic, state-aware, and contextually intelligent. Now that we understand how the MCP lifecycle works, let's talk about the key components we will implement in our MCP server example and how each part fits into the MCP server architecture. Here's the overall project structure that we'll use. Let's break this down step by step. We'll start with server initialization. This happens inside two key files, MCP app and MCP instance. The MCP app file is our main entry point. It's where the server starts up, initializes configurations, and launches the MCP instance. Inside the MCP instance, we define how the MCP server is set up, connecting all the components like prompts, resources, and tools loaders. It is responsible for configuring the server's core behavior, setting up communication channels, and preparing it to handle incoming MCP requests from the model or client environment. In this example, we are defining a single instance of the FastMCP server using its default configuration. We'll use this instance with annotations when creating tools, resources, and prompts. Next, we have our route and handler definitions, which are spread across three main files: MCP tool, MCP resource, and MCP prompt. Let's start with MCP tool. This file contains all our tool implementations. Tools are special functions that extend the server's capabilities, allowing the model to perform useful actions like searching data, sending messages, or interacting with external services. Each tool defines a clear input, output, and logic for how the MCP server should process that request. In our example, we have implemented tools, a text search chat tool and an email sending tool. The first tool is text search chat tool, and it's designed to search through our Codoris knowledge base, which is stored in a text file inside the resources folder. It takes a single parameter called query, which is just the search term entered by the model or user. The search is case insensitive, meaning it doesn't matter whether the input is uppercase or lowercase, it'll find all relevant matches. The tool scans the knowledge base line by line, looks for matches, and then returns a structured JSON response. So the output includes the original search query, a list of matching lines from the text file, and a count of how many matches were found. In short, this tool turns the MCP server into a lightweight information retrieval system, allowing the model to query stored knowledge instantly. Next, we have Send Email tool. This one is a bit more interactive. It uses a predefined email template from the resources folder to send out newsletter emails. The function accepts several parameters: subject, which defines the email subject line; recipient, which is the recipient's email address; and optional parameters for SMTP server and SMTP port, which default to Gmail's SMTP configuration. The tool pulls the body content from the email template text file, formats it as needed, and sends it out using the configured SMTP server. Once the email is sent successfully, the tool returns a Boolean value, true if the email was sent, or false if something went wrong. This makes it super easy for the model to send dynamic, template emails without ever leaving the MCP environment, and it showcases how tools can go beyond data retrieval to perform real-world actions. Both of these tools are registered with the MCP instance using the @MCP tool annotation, which means they automatically become available to the model as callable functions through the MCP protocol. Together, they demonstrate how easily you can build custom tools that make your MCP server more capable, more interactive, and more intelligent. Then we have MCP resource. This file handles resource loading. Resources are the data elements or knowledge files that MCP server can make available to the model. Think of them as the server's built-in reference materials like text files, JSON documents, templates, or even structured data that can be accessed whenever the model needs more context. In our example, we've included a single resource, a company information file called Codorus.txt, which contains knowledge about the organization. The MCP resource script defines how resources are loaded, formatted, and served to the model through the MCP interface. Let's take a closer look at the code. We use the @mcp.resource decorator. This is similar to the tool annotation we used earlier, but instead of registering an action, it registers a resource that the model can query. In this case, we are registering a resource with the URI, meaning that when the model requests that endpoint, the server will return the contents of our Codorus text file. Inside the function, we define the logic for reading the file from the resources directory. If the file exists, its content is read and returned as a string. If the file is missing, we send a fallback message, no knowledge base found, prompting the developer to add the missing resource. This simple yet powerful setup turns any local file into a live resource endpoint inside the MCP environment. So that's how we define and register resources inside the MCP framework. It's clean, lightweight, and incredibly flexible, allowing you to expose text files, templates, or even structured data as part of your model's knowledge ecosystem. And finally, we have MCP prompt, which defines the prompt templates that the model uses to structure its interactions with the MCP server. Think of prompts as predefined conversational templates or structured instructions. They tell the model how to ask for something, whether it's fetching data, triggering a tool, or simply greeting a user. In other words, instead of the model trying to figure out the phrase every time, prompts give it a consistent and predictable way to make requests. Let's look at the code for our prompt. We use the @mcp.prompt decorator to register a new prompt with the MCP server. In this case, we name it user greeting. Inside the function, we define a simple Python routine that takes a parameter, name, which defaults to learner if no name is provided and returns a friendly message. So whenever the model references this prompt, it can dynamically fill in the user's name and respond with a consistent, friendly greeting, perfect for onboarding or conversational flow. Alright, now that we've built our MCP server and defined all the components, let's move on to the demo of our MCP server. We're going to start the MCP server along with the MCP inspector. MCP inspector is a visual interface for testing and inspecting your MCP setup. Once MCP server is up and running, we'll open the MCP inspector in our browser available at localhost. The MCP inspector allows us to connect directly to the MCP server and test our prompts, resources, and tools through a clean graphical interface. Alright, now that we are connected, let's start exploring the different tabs available in the inspector. We'll begin with the Prompts tab. Here you can see all the prompt templates defined in our MCP server, including the user greeting prompt that we registered earlier. Let's test it out. When we invoke the prompt, it asks for a name parameter, which defaults to learner if we don't provide anything. If we run it as is, the model returns, hello learner. Welcome to Codorus. Now we'll enter the name, John, and run it again. The response updates to, hello John. Welcome to Codorus. Simple, clean, and dynamic, that's how MCP prompts bring structure and consistency to model interactions. Next, let's move over to the Resources tab. Here we can list all the resources exposed by our MCP server. You'll see our Load Codorus Details resource listed. When we open it, the server responds with the content from the content file inside our resources directory. This is a great way to make reference documents, templates, or company data directly available to the model, without relying on external APIs. Let's start with the chat tool. This tool lets the model search through the Codorus knowledge base using a query string. In the query field, let's type the word development and run it. The tool responds with a JSON result that includes all the matching lines from our knowledge base file, along with the total count of matches. This shows how the MCP server can act as a knowledge retrieval layer, letting the model fetch context from local data sources on demand. Next, let's test our Send Email tool. In the subject field, I'll type Codex Academy Newsletter. For the recipient, I'll enter codeoris@gmail.com. The SMTP server and port are already set to their default values, so we'll leave those as they are. When we execute the tool, the MCP server uses the predefined email template from our resources folder, sends the email, and returns a response of true, indicating success. If we check our inbox, there it is, the newsletter email has been successfully delivered. That confirms that our MCP server is not just responding to text-based queries, but can also perform real-world actions like sending emails. And that wraps up our MCP server demo using the MCP Inspector. In this video, we explored how the MCP server brings together prompts, resources, and tools into a unified ecosystem, allowing the model to retrieve data, run actions, and interact with external systems seamlessly. If you haven't watched our previous video on Model Context Protocol fundamentals, be sure to check that out first. It covers the core concepts and setup. And in upcoming videos, we'll dive deeper into building custom MCP extensions, connecting to real-world APIs, and enhancing model intelligence through context orchestration. Thanks for watching. Don't forget to like, share, and subscribe for more deep dives into AI engineering and MCP development. See you in the next one.